Hello and welcome to The Explainer. Let's be honest, we're asking AI to do more and more for us these days, to write complex code, whip up detailed reports, you name it. But as we keep piling on the requests, a really critical question pops up, and it's one that some new research from Distill AI decided to tackle head on. Just how much can an AI really handle before it starts to break?
You know, think about it like this. You've got way too many tabs open in your brain. Someone's asking you to remember a phone number, you're trying not to burn dinner, and you just hit a wall. You start forgetting stuff. Well, it turns out our fancy large language models have a breaking point too. And today, we're going to find out exactly where that point is. So here's the game plan for this explainer. First, we'll talk about why this whole instruction overload thing is a much bigger deal than you might think. Then, we'll see how the researchers put these AIs to the test. After that, we'll dive into the 3 really interesting ways these models fail. And of course, we'll cover the surprises, the weird biases, the trade-offs, and finally, the big takeaway from all of this. All right, first things first, the core issue here. You see, as we get more ambitious and start asking AI to juggle, dozens or even hundreds of instructions at once, the risk of it getting something wrong, it's not just a possibility anymore. It becomes a major operational risk.
And I want to be clear, this is not just some techie glitch we're talking about. When an AI can't follow instructions properly, it can cause some serious real-world chaos. I mean, you get customer service bots that literally invent company policies out of thin air, or automated systems giving out advice that's just flat out wrong and even dangerous. The stakes are incredibly high. So to really get a grip on this problem, researchers at Distill AI built a brand new tool. It's a benchmark called ICE-Scale, and it's designed to do one thing: to scientifically find the cognitive limits of these AI models. The IF-Scale benchmark is basically an AI stress test. It's designed to systematically pile on the cognitive load, by feeding a model more and more instructions, and then just watching to see precisely when its performance starts to dip, or when it just falls off a cliff completely. And the method they used is, honestly, brilliant in its simplicity. So first, they created a list of 500 different business keywords. Then they asked the AI models to write a standard business report. Simple enough, right? But here's the catch. The report had to include a specific list of those keywords. They started with just 10 keywords, then ramped it all the way up to 500. And then they had a system to automatically check how many instructions the AI actually followed. So what happened when they cranked up the pressure? Well, this is where it gets really fascinating. It turns out AIs don't just fail at random. The research found 3 very distinct, very predictable patterns of failure as you pile on the instructions. But before we get to the patterns, here's the big headline result. Get this. Even the absolute best model in the test, Gemini 2.5 Pro, could only manage to follow about 68% of the instructions when it was given all 500. That means it failed on almost a third of its tasks. It just goes to show even the heavy hitters really struggle under pressure. Okay, so the first failure pattern is something they call threshold decay. These models are amazing. They're nearly perfect as you add more and more instructions, right up until they're not. They hit a specific point, a threshold, and then their performance just suddenly and catastrophically falls off a cliff. It's like a Jenga tower that's perfectly stable until you pull that one last block. And you see this pattern mostly in models that are famous for their reasoning skills, like Gemini 2.5 Pro and OpenAI's O3. It's like their complex, step-by-step thinking lets them hold on for dear life. But man, when they go fast. They have a very clear, very sudden breaking point. The second pattern is called linear decay. Now, this one is way less dramatic, but it's just as important. With these models, performance just drops in a steady, predictable line. For every 10 new instructions you throw at it, you can pretty much count on a small, consistent drop in accuracy. It's like a slow, steady leak in their cognitive tank. Models like GPT 4.1 and the newer Claude 3.7 Sonnet fit right in here. With these, you don't get any sudden collapses. It's just a predictable, kind of sad, steady decline as the job gets hard. And the last pattern is exponential decay. This is basically the exact opposite of those threshold models. These AIs get overwhelmed almost right away, their accuracy plummets with just the first few dozen instructions, and then it just
bottoms out. It continues to perform, but at a really, really low level. This group includes models like Llama 4 Scout and Claude 3.5 Haiku. But now for the biggest shocker of the whole study. GPT-4o, OpenAI's super hyped flagship model, celebrated for its speed and its power, it falls right into this category. It showed shockingly weak performance on this specific kind of task. A real surprise. All right, moving on to section 4. This is where we get to dig into the really juicy stuff beyond just the failure patterns, all the fascinating little surprises and trade-offs the research uncovered. So this table just lays it all out, bare. At the top, you've got Gemini 2.5 Pro, the winner, with almost 69% accuracy at 500 instructions. But hey, look at Grok 3. It's a really strong contender, not that far behind. And then you look down at the bottom and see GPT-4o. It goes from a pretty good 94% with just 10 instructions down to a measly 15% with 500. That is a massive, massive drop. So this leads to a classic question that every prompt engineer asks, right? If you know the AI is probably going to fail, can you at least game the system? Can you put the most important instructions at the very beginning to make sure it gets those right? Does the order actually matter? Well, the answer is yes, but it's really weird. Models do tend to pay more attention to the first things you tell them, but this bias, it's not consistent. It actually gets strongest in the middle of the pack, somewhere around 150 to 200 instructions. It's like this is the struggle zone, where the model is really trying to keep up, but it's starting to fail. Then, once it's totally overwhelmed, the bias just disappears. It just starts forgetting things at random. And this right here perfectly illustrates the critical trade-off that every single developer has to deal with. Sure, Gemini 2.5 Pro was the most accurate model, but it was also one of the slowest. On the flip side, you have Grok 3, which delivered really high accuracy, but with super low latency. It was fast. So what do you need? The absolute best accuracy, no matter how long it takes, or a good balance of accuracy and speed for your app? The research also found that when these models fail, they almost always fail in one particular way. They make omission errors. What that means is they don't get the instructions slightly wrong, like they don't use the word accountable when you ask for accountability. No, they just forget to include the word accountability entirely. They drop instructions. They don't just mess them up a little bit. Okay, so let's bring all of this home. What's the final takeaway? What is the single most important lesson we can learn from this deep dive into the cognitive limits of AI? Here's the bottom line. There is no single best AI model out there. It just doesn't exist. The right choice completely depends on what you need it to do. If you're drafting a complex legal document, yeah, you might want to pick the slow but super accurate Gemini. But if you're building a real-time chatbot that's juggling tons of users, the fast and pretty darn accurate Grok 3 might be a way better choice. It is all about that balance. And that leaves us with one last big provocative thought. This research proves that every single model has a cognitive breaking point. This isn't just a bug in one piece of software. It seems to be a fundamental limitation of the tech right now. So the real question for the future isn't just which model is better. It's how on earth do we build truly reliable AI systems, knowing that at their core, they will always have a limit to how much they can handle at once. That's the real challenge ahead.